Hello, good afternoon, everyone. I hope that you guys are doing all right. Welcome to our 8th lecture of the course. So let me start by asking if you guys have any questions about the assignment, which is due tonight at midnight. We have a few of you, I think, last office hours. Probably most of you are okay. Just let me comment on something I noticed, at least with some of the code I saw. Let me see if I can share the assignment description. Something that is a little bit important to take into consideration is the following. In the part 3, where I saying, please create one function for each of these steps, I'm in particular noticing that some of you may have not realized that the reading data should be a function. So part 3A, which it will be a function which receives an argument indicating the month and year to process, and select the corresponding records, let's say, on the reported day from the data, and print it as Fermi process and returns this data. Again, this should be a function. So what I'm trying to say is, if I saw cases where, for instance, people was putting the reading data in the utility files, but as I usually refer as an orphan call to the function. And that is not good, because a couple of things. On the first hand, every time that you source the utility file, that line is going to be executed, and you may have noticed, depending on the day and the time of the day, during the day that you load the data, it can be a little bit slow. But more importantly, perhaps, is that that will remain as a global variable floating around. So that should be part of the reading data function. Okay, that's the only thing I think I have noticed. Again, in some of, I'm not saying everyone is doing this, but in some of the codes I saw, and you know, in a modular approach, that shouldn't be the case. It should be everything encapsulated in the reading data function. Even if you ask me, the load in the library, because the only place where you are going to use the COVID-19 analytic package is within the reading data function, I will even place loading the library within that reading data function, so that that library is not loaded unless you are actually invoking that reading data function. Okay. I think we have a question. Let me see. So there are two source commands that you will be using, Shada. It's a good question. The source of the utility file should happen within the process store coded main driver script. But then when you do the testing, when you actually want to test that you are getting the answers, you are still going to source your main driver script, which will source your utility files and then give you access to the different functions. So let me put it this way. There will be one source command depending on what you are looking at. If it is the main driver script, there will be the source of the COVID, how we call it, COVID utility files. If you are at the terminal in the R console and you want to test your script, you will source the process store COVID.r file and then call your process store data. The process store data, well, the main goal here is to be this function that we define. Actually, it's a little bit of a reverse approach, bottom-up versus top-up approach. Is the function that we actually create in two, which is a wrapper function that invokes each of these functions from three. Will that make sense? No problem. Any other questions about, again, assignment number 3? All right. So if there are no questions, okay, let's go back to the lecture. Okay, so last class we were talking about file I/O. Any questions about that? did it make kind of sense what we were talking, what we discussing, the points that we emphasize? I hope they did. And what I want to finish today and then quickly move into a different topic is the standard file formats. And I believe we ended here talking a little bit about the different ways that we have for storing data. And the real good ones are what we call standardized file formats. And the one that we're going to be talking today is NetCDF. So NetCDF stands for Network Common Data Format. Is used across many different languages and disciplines, which make it really, really appealing for sharing data with the community, different communities, and even journals. So it's self-describing, as we discussed. We can include metadata. So what comes next is we're going to see how the model of storing the data is for these file formats, and then how we will do it in R, of course. The NetCDF has several versions. There are a little bit older versions and the newer versions, just to make set the basics for the classic data model. Contains basically three entity types: variables, which are basically where we can store the data, and the nice thing of these variables is they can be multidimensional. And they can be of different types. They can be characters, they can be bytes, short, integers, float, or double. So all type of numeric values in particular. Dimensions, these are associated to the arrays, to the multidimensional arrays. That's the main target of NetCDF. So the dimensions basically describes the sizes of the arrays. And then attributes. So the attributes are complementary information to describe this variable. So it's kind of where the metadata shines. And we have attributes that can be global or can be applied to a particular dimension or to a particular variable. We can even put units in these attributes. So let's see how it looks in a schematic way, and then we see how we implement this in the code. So let's start thinking about, we have some binary data, and this binary data you don't need to worry about, but it can be a matrix or an array, a vector that you created in R. And then this will have associated a particular type. It can be, because we know arrays are homogeneous, so it can be either all Booleans or all integers or all decimal point numbers or all characters for what it matters. So we're going to pick a name, obviously, to this object. But then we will have dimensions associated to this. And the simplest case when we're talking about one-dimensional array, a vector. But this could be a matrix, as we saw in other examples. So you can have several dimensions. In general, dimension 1 and dimension 2 represents a matrix, but you can even have a third dimension, and you will be talking about a tensor, for instance, or something more generic with more dimensions if you need. Then each dimension can have a name, because let's say that we have multiple of these objects, so then we can reuse this dimension for different objects. So at the same time, as I was saying, we can have attributes associated to the data or associated to the dimensions as well. And so this is kind of the basic building block of the type of NetCDF file. A variable containing data, which can be, as I say, where NetCDF actually writes is for multidimensional arrays, but any kind of data that can be, put in that way will work. That is our main working unit, or elementary unit, if you wish. So you can have then multiple of these units in a file. And then finally, within the file, you can have file attributes. Like, for instance, who was the creator of this file? When was the file created? For which purpose? If this was data collected from where, those kind of things. So the attributes at the same time, notice this, I can say, okay, if I had these dimensions and they repeat all across the objects in the file, what I can do is, okay, put at the level of the file, and then keep those as global elements for the file where it can be referred by each of the objects that I have. So that is the most generic, more general point of view for how the NetCDF file is composed. Any questions about this? All right. And of course, this file will have a particular file name. No question about that. So let me mention something else. I mentioned NetCDF has been around for a while, almost 20 years, not 20, but 15 years or something like that. maybe 20 years. But on 2008, there was a new release that basically allow NetCDF to gain in certain properties, for instance, compression, chunking, and parallel I/O. So this is completely back compatible, so you can still read NetCDF files that have been previous to that version. But that's why you are going to be seeing the package that we are going to use is called NCDF4, and that is because on version 4 there was a kind of breakthrough in several elements, but represented by the model I just showed you. Now, there are some conventions in NetCDF, and these are the ones that allow us to include units, which is something super useful, especially if you are talking about physical quantities that, depending on which metric system people uses, you refer to them as centimeters or inches or whatever. That is something that is quite relevant, quite useful. So there are a list of conversions that you can follow. There's even a link to see which words or abbreviations you can use. So it's quite easy to include that include that information in your data. So let's take a quick look at how creating a NetCDF file will look like in R. And just to, as I mentioned, we are going to use this library NCDF4. NCDF4 is not one of the default libraries that come with R. So if you want to use it, you need to install this library, okay? So in this case, I assume that the library is installed in the machine, and this is a piece of code. Basically, load the library. Then what I'm going to do is I'm going to store a matrix of 10 by 15 elements. So I define how many points I want in the X dimension and the Y dimension, for instance. And then I create a matrix just, for the sake of creating some data. So my matrix goes from 1 to 10 times 5, 15, from 1 to 50, sorry. And then number of rows is given by the number of points in X and the number of columns by the number of points in Y. Now, this happens all at the level of R. We haven't said anything so far about how this maps into the NetCDF structure of the file. This is where things start to get NetCDFied. So first thing is we're going to define what is the dimension associated to the matrix in X and in Y. So for that, we use ncdim_def for defining the dimension. And we are going to associate it with the label X, the variable X, is going to be in units given by meters. It's going to be as double. So by default, X is going, in this way we created, is created as an integer in R, but I want to store as double. And then you can even give a long name. So saying, okay, this is the measurement between points A and X horizontally or something like that. So you can have a description if you wish for that dimension, the attributes we were just talking about. Y dimension exactly the same, but instead of using X, we use Y. Right? Now comes the place of creating the variable, meaning the place where we're going to actually store the data within the matrix. So for that, I'm going to create a variable called a.definition, and it's going to use nc_bar_def. So this defines the variable within the NetCDF file. In this case, it's going to have the name of the variable A. In this case, it's a unitless, but it could be temperature. So in that case, it could be Celsius, Kelvin, or Fahrenheit, or pressure with pascals, or whatever unit you want. And then what comes is the dimensions. And the dimensions are the dimensions that we just created for the NetCDF file. And they should be given as a list. So it's list of xdim and ydim. So that is the process of creating the variable. Now comes the process of creating the file. So in this case, I'm going to call this ncout because it's the output for the NetCDF file. I'm going to use the function nccreate, the name of the file, test.nc, then what definition I want to put, what variable I want to put. I want to put the variable associated to the matrix, so a.def. And then this label is to actually enforce to use version 4 of NetCDF. So force version 4 equal true, make us sure that we are we're saving the file as NetCDF version 4, which is the modern version of NetCDF. Any questions about this? So one thing that we haven't done yet, and this is important, is we haven't actually placed the data inside the file. All what we have done here is to basically prepare the workflow, but data has not been transferred. We created the dimensions, we created a space for where we are going to put the data inside the file, and then we created a file associated with this, but we haven't actually put anything inside the file. Where that happens is in the next lines. NC bar put. So NC is for NetCDF, variable, and put is actually put inside the file. So what we need here is the handler of the file. That's what we define just here. We can call this the handler, what points to the file in the hard drive. The variable that we want to define and the actual data. So this is just like preparing a drawer with the right number of spots for all the data we need to put in there. This is the process where we actually dump the data inside the file. On top of that, as I said, this is a self-describing file format, so we can put some metadata. We can add some additional information. So this goes through global attributes. So we can say NC attribute put is for putting inside the file, and then 0 just corresponds to be metadata, the handler of the file, and then the title could be, so these are establishes records, if you wish, or fields, title, my JSON data, institution, sign it, you can put your name, and so on. Now, something which is quite important, we talked about this, I think, last class, is to close the file. So NC close, NC out, the handler of the file again, is the process that guarantees that all the data has been transferred, the file is closed in perfect condition. Okay? Any questions about this? All right. So that was the process for saving the data into a NetCDF file. Let's see how we'll read the data. Of course, we're going to need the library, NetCDF4. And in the same way that we define an NC out handler, we're going to define an NC in, is for input in this case. We are going to use NC open for opening the file, and then the name of the file. Okay. Now, when we do that, and if we look at the variable that contains whatever we wrote in this file, it will give you a bunch of information. Actually, it's a very rich dictionary sort of structure, if you wish. And it tells you, okay, the format is NC, NetCDF format, NCDF4. The variables is a float, means it's a decimal point number with 2 dimensions. The units for A is unitless, but then the dimension has size 10 and 5, as we indicated, with units in meters, and then some global attributes saying, okay, whatever we brought there. Okay. What else can we get? So far we got the pointer, the handler to this file that we created. How we recover the data that we put in there? Well, in the same way that there were NC different functions underscore put, we have NC different functions underscore get for getting the data from the file. So let's say that I want to get the value of the dimension X. What I will do is, okay, NC bar underscore get from the handler of the file, and then the variable X. That's how we define, is also explicit here. The dimension, if you don't know the name a priori, is called dimensions X and dimensions Y, and then A is the variable. So NC bar get NC in X returns whatever was the values for the dimension X, and then we can print X and you get the 1 to 10 values. If we want to get the matrix, which call A, then we do NC bar get NC in A, and then we get the matrix, the dimensions, we can look at what the matrix contains. Okay. If we want to get some of the metadata, we can use NC attribute get, and then the handler 0 is for the global attributes of the metadata, and then any of the keywords that we want, institution or values or things like that. Hash at means if there is an attribute present or not, so you can query if there are attributes. So it's quite easy to get the data back and forth from the file. Any questions about this? Okay, so this is a quick summary of the lecture that we discussed last class. I won't go through this. I think most of the things we talked last time, but the bottom line is try to minimize the number of input-output operations. I showed you a kind of trivial example last time, but believe me, you may hit into these problems if you do a lot of data manipulation. Try to use binary whenever it's possible, especially if your data are numerics or floating point numbers, decimal point numbers. Try to use a standardized file formats like NetCDF or HDF. I have a few more slides that I'm not going to go over about HDF, which is a different standardized file format that you're more than welcome to look at it and ask me if you have any questions. NetCDF is quite easy to use, especially in R. In other languages, it's a little bit more convoluted, but in R, you have the luxury of being able to use it almost very simply, I would say. Okay, any questions about this or the previous class? While you guys think, if you have any questions, I'm going to switch to my other set of slides already posted in the website. And the idea, this set of slides will take us probably today and next class, is just overview of how to perform computational statistics in R. As I told you at the very beginning of our class, our course, R is super powerful for running statistics, and is one of the very strong elements in R. So, sorry, I'm looking for my chat, which every time I reshare, I keep saying this, but every time I reshare the thing, it soon moves my windows all over. Okay. So as I was saying, R is very, very strong for running any kind of statistics. So that's why I want to show you, and in particular with some very powerful functions that R brings along, how to do some basic stats. Usually in other courses, I spend weeks talking about running statistics. And as I say, the plan for what is next in the course is going to be, so we're at lecture 8, lecture 9 probably is going to finish this batch of statistics. And then lecture 10 and 11, I was planning to do visualization for professional plotting, and then visualization for interactive manipulation of data. And then lecture 12, it can be, I don't know, it's up to you guys. If you guys let me know something in particular, like topics we can cover easily is machine learning, neural networks, high performance R. If you don't have any particular preference, I can't just pick one for you, but if you guys have a particular preference or a topic that you would like to see covered, in other courses I do survival analysis, but I don't think it's too interesting for you guys. I can do also hypothesis testing, dive more into statistics. So there is a little bit of room for customization of what comes next. So again, if you have any particular interest, just let me know. If not, I may just do high performance R, or we can also, if there is no interest in doing interactive visualization, we can do machine learning. Again, let me know if you guys have any particular topic that you are interested in. So, so this part of the material will be a quick review on probability and statistics, and some examples how these things are implemented in R. So as I say, R has tons of different functions already included in the program, in the language, to do statistics. The summary function, which I believe we saw a couple of lectures ago, is an example. Other functions like mean, standard deviation, variance, minimum, maximum, range, quantile, find numbers, and probably more if you start to dig into different packages. So some examples is even the data that R includes. So if you do data, you can look at different collections of R data sets and pick, for instance, their percentages and take a quick look at that. You can ask for the summary of these data frames. You can ask for the find number description of these data frames. So all this is part of R. I always like to include these graphics to just remind all that some concepts, when they're even matching in the number description, not necessarily matching the conceptualization of the quantity. So it's important to, even when one has all this very handy, to always be mindful of these numbers and what they represent and mean for us. But again, that could be a completely different lecture talking about just interpretation of statistics. One important element, and this will be relevant to our new assignment, which we are going to be talking about today, is that R also brings a lot of standard distributions and in different flavors. So typical standard distributions or probability distribution functions that you will see is uniform distributions, normal or Gaussian distributions, binomial distributions, Poisson distributions, and many others. There's a long list. And if you're looking for a very weird distribution function, there is probably a package that implements this for you. The important thing, though, really important thing is for each single distribution function you can think of, R brings along four associated functions. One is what we call the actual probability distribution function. This usually is referred as the density distribution function. The cumulative distribution function, which usually is what we refer as the probability of the distribution function. The quantile, which is you can think about the quantile as the function that, given a probability value, it returns which value is such that it returns that probability value. And then this one, which is the one that is going to be really, really interesting for us in this assignment, is the random number generator function. The random number generator function, what does is it samples randomly or pseudo-randomly, for being more explicit technically, random numbers sorted or drawn from a given distribution function. So if I give you, okay, give me 5 random numbers from a uniform distribution, which ranges from A and B, the uniform distribution is basically flat. So those 5 numbers will have whatever value that random uniform distribution has. Now, if I ask you for a normal distribution function and pick 5 numbers randomly, then those numbers will follow the Gaussian distribution function, and so on. So basically, the selection of, or random selection of points or values is done through the selection of random values given a particular random distribution function. Now, these 4 functions associated with each probability distribution function I just mentioned are characterized by the letter D for density, P for probability, Q for quantile, and R for random number. So if we are looking at the normal distribution function and we want to compute the density of the normal, we will use the function d norm. If we want the probability, we use p norm. If we want the quantile for the normal distribution function, we'll use q norm. If we want random numbers generated from the normal distribution, we are going to use r norm. If I want random number from the binomial distribution, I'm going to use r binom. If I want random number from the Poisson distribution, I'm going to use r pois, and so on. Okay, I had a few examples for you, but please do let me know if you have any questions about this. I'm going a little bit fast. I'm assuming that everyone is familiar with statistics. We are not going to dive too much into the concepts. It's a field that I really like. I could spend hours talking about that, but this is not what the course is focusing right now. It's more about the techniques and how to use it through R. But if you guys have any questions or something is not clear, or you want me to go much in details in a particular area I have mentioned, just do let me know, okay? Let's take a look at a few examples, but again, my offer is still open. Whenever you guys have questions or thoughts that you want to express, feel free to do it, okay? So a few examples. Let's say I want to compute the normal distribution with the default value of mean equal to 0 and standard deviation equal to 1. So this is, you have to keep in mind the Gaussian bell, if you want the Gaussian shape, which is centered at 0 and standard deviation 1. So if I want to get the values, for instance, I can do d norm, and I can evaluate the Gaussian distribution at -2, 0, and 2. And what you will see, something that you will expect, is the shape is symmetric with respect to 0, so -2 and 2 has the same value, and this is the value at 0. And that corresponds, as I say, to the Gaussian shape. Now, if I want to shift this Gaussian shape and put the mean at 1 and standard deviation 2, increase the width of the Gaussian shape, then I can do the norm, the same vector where I'm evaluating the distribution function, the density distribution function, but now the mean is set at 1, that's the next argument, and the standard deviation is set at 2. All these conventions which you can get very easily by doing hel d norm, and it will tell you exactly what goes where, and you can even put explicitly mean equal 1, SD, standard deviation equal to 2. If I want to compute the quantile of the normal distribution function for a value of 2.5%, then I can just do q norm of 0.025. And that gives me a value of -2 almost. So 2.5% probability in a distribution function is almost at the very left of the negative range of values. If I want to compute the probability of a given distribution function, of a normal distribution function with these values, -2, -1, 0, 1, and 2, remember this is cumulative, so you can see the result by and how it's increasing. So R2 is almost a 97.8%, 97.7% probability. So that is the area under the curve, just to bring back some memory from statistics. Any questions about this? This is just to show you how to use one of these, a few examples to show the different associated functions to the normal distribution function. We saw the D norm, Q norm, P norm. What I'm going to show you in more detail is the random number generation function. So let's say I want to generate 5 random numbers from a default normal distribution. When I mean default, I'm assuming mean equal to 0 and standard deviation equal to 1. Then I do R norm, and then R returns 5 random numbers generated from the normal distribution function. If I want 5 random numbers generated for the normal distribution, and this is a little bit of convention with a mean of 100 and a standard deviation of 50, then I will do R norm 5 numbers with mean of 100 and a standard deviation of 50. And as I was saying before, if I want now 5 numbers generated from a Poisson distribution with the parameter that characterize the distribution to be lambda, the rate of change in the Poisson distribution of 100, then you do RPOS, and the default value, the value that you want to use for the rate is 100. Okay, so that's how we generate random numbers using different distributions. Any questions about this? And again, this combined with a little bit of basic probability concepts are what is going to be part of our assignment for this week. Okay. Let's move on. Okay, so I'm going, yes, Ina, can you restrict R norm to give integers? Well, not R norm per se, but you can use as integers. So when you do, let's go back to one of these examples. When you do R norm, you can basically truncate these numbers with different techniques. You can do as integer, you can use, I think there is trunc for truncating, which will give you just the integer part, or you can do, which is the function I'm trying to remember now. There is a function that I think is round off or floor to give you the next larger integer. So not the function itself, but you can basically use another function. Now, one thing that is important to mention related to this question is the normal distribution function is what we call a continuous distribution function. And that's why you are seeing real numbers. You're seeing numbers with decimal points, while Poisson or binomial distribution functions are what we call discrete distribution functions, and that's why you see integer numbers here. Okay, but to answer your question, Sina, not necessarily with the R norm function, but manipulating sometimes the result of the manipulating, I mean truncating the decimal part of the number or rounding off the number. That's how you make it just integers from that sampling. No problem. So what comes next is a family of functions that are super useful, super powerful, not necessarily tied to statistics. You can use with your own event functions, your own defined functions. But I took the case of doing some stacks for showing how to use it. These are called the apply family functions. And the idea here is that you can get really high performance with these functions, and sometimes you can even parallelize very easily your codes, meaning running in several cores or several computers, by using some how to say, upgraded versions of these functions. Okay, but these are super powerful functions, are at the level of vectorization, so very, very optimal in the use of resources. So, and there are a few ones that we are going to be discussing. There are a couple more that I have included, but these are the most relevant ones, I would say. LApply is a function which apply a function to an element in a list of a vector. SApply is very similar to LApply, but simplifies the results. So instead of returning a list, it returns a vector. Apply is for matrices or arrays, multidimensional arrays. The appliance is when you usually use for data frames, let's say, and NApply is for matrices, but also allow you to put multiple arguments in the function. So we are going to see examples of each of them. The idea behind is think about a list. Think that in each list you have an element where you want to apply your function. So for instance, I have a list with different entries of composition of proteins, and then I have a function that analyzes each protein. But I won't allow you to take your function and apply it to the list as if it were the sum function applied to elements in a vector, because it doesn't know a priori the structure of the list. So either you need to modify your function to process element by element, which is going to be sort of a for loop process, which, as you saw in the last assignment, is not the most efficient, neither the most elegant way of doing it. So instead, we can use the lapply function, which we are going to say, okay, take this list and then take my function, and the function lapply, we apply my function to each of the elements in the list. That's the main idea. It gains in performance, it gains in clarity of the code, and as I say, is definitely the way to go. So let's take some examples. We're going to look at the lapply function. For doing this, we're going to be playing with some random samples and with some things. And again, some examples are a bit artificial, but I hope they can communicate the message behind. So, so the idea here is we're going to generate, so we are creating a function here which basically computes the mean of n random numbers. And these are random numbers generated from the normal distribution. So this function, basically, I pass into the function how many random numbers I want to generate, and I compute the mean value. If this is correct, the mean value should be close to, what do you think? This is the normal distribution again of the Gaussian distribution. It's kind of self-explanatory. The mean value should be close to the mean value that defines the normal distribution. And if not, correct, that's right, Peter. So in this case, because I'm not specifying anything, the default value for the mean of the normal distribution is 0. If I would have put a different value, that will be the value. But let's say that I want to run this. So this function, I can put 10, and then it will return a value. But let's say I want to run this experiment multiple times. I want to run this function with the value of 1, 10, 100, 1,000, and 100,000. And now I have this vector with all the values that the argument n of the function will take. So one way, as I was saying before, is I could loop over these elements and pass each of these entries as an argument to the min.n.rnorm function, as we did in assignment 2 for the last part, and that will do it. But as I say, it's not the most elegant way of implementing that, neither the most efficient way in terms of performance. So instead, we can do exactly that by using lapply. And so lapply will take your vector in this case. It can be a list. We're going to see that in a second. And then apply the function that we just defined. Again, this function is defined on a line, but you can put the curly braces and make it look pretty and put your descriptions and documentation and everything else. So what happens here is when I apply lapply, then lapply returns 5 elements in a list. That is because lapply returns a list by default. And now the first output is the one that I get by calling the min.n.rnorm function with value of 1, pretty off from 0. But as you can see, as the number of values, meaning the number of random numbers considered, are increasing, as Peter mentioned, this value gets closer and closer to 0. This is nothing else than a way to demonstrate, by the way, numerically, the law of the numbers, of the large numbers. If you remember this theorem from statistics, is basically showing you that as you increase the number of samples in your statistical sampling, then this converges to the mean value of the normal distribution. And that's exactly the case here. But the important element, the important technical element is we are applying the function we just defined to each of the elements in the vector ns. And because we use the lapply function, we are getting this back as a list, as you can see here. Okay. Again, think about how you will do this without using the apply function. You need to go and iterate basically in each of these elements and pass that argument into the function. Let's look at another example, the same idea, but implementing this in 2 steps instead of 1. Okay, I keep my same vector, ns, 1, 10, 100, 1,000, and 100,000. And then I'm going to use lapply twice instead. So I'm going to use For generating my random numbers, I'm going to take LApply. I'm going to use the R norm function and then the ns vector. And this, what it will do is it put in the random numbers a list containing 1 random number, 10 random numbers, 100 random numbers, 1,000 random numbers, and 100,000 random numbers. So it's a list with 5 entries, but each entry has different numbers randomly selected from the normal distribution. Now, my second step now is to apply LApply to the elements in the list that we just generated and just use the mean function. So instead of using my own function, I'm using R norm and mean used twice with LApply. So in this case now, LApply will go into the entries of random nums and apply mean. And when I get that, of course, the numbers will not exactly match because this is random. So the numbers will change slightly, but you see the trend. The trend is, again, as you get to the large values of random numbers, it gets closer and closer to 0. Okay, so 2 examples of achieving the same thing using LApply, but in slightly different ways. Any questions about this? All right. Let's take a quick look at SApply now. So SApply is very similar to LApply if you follow the line of thought, but it will return the result simplified, meaning that if possible, instead of returning a list, that's what we were seeing here, a list with 1 entry. In some cases, it can be beneficiary for us to return the list, but in other cases, we may want just to have a vector so that we can operate with that. So again, I have in my number of samples vector here, 1 to 100,000, my random numbers exactly as before, and now instead of using LApply for the last point, where we compute the mean, I'm going to use SApply here. And if I look at the means now, I get numbers. And this is useful because now I can operate with them. I can, for instance, compute the means square, and I get the numbers just like that. Okay, so the only difference between LApply and SApply is that the output of SApply, instead of being structured as a list, is structured as a vector. Okay. Any questions about this? Okay. This is a performance tip. As I told you, there are different variants or variations of these functions. One that is quite similar to SApply is BApply. The difference with BApply is, as you notice, when I'm calling SApply, I'm assigning this to a vector. But if you use BApply, you can add 1 element in the function, which is the vector. For instance, it will be means. It's a vector that is already created somehow, and it's where the data is going, the result is going to be stored. This is important when you're looking at a large, very large vector or a number of elements in the list, because that will help you in making the code substantially faster and more memory efficient for large outputs. If you're not talking a really large output, that's okay. You are fine doing SApply. But for things that are order of millions, 10 millions, 20 millions, or 100 millions, then you may want to consider the BApply implementation of SApply. This is similar to, I think we discussed this a couple of lectures ago, when we initialize a vector with a number of spots versus copying a vector or appending to the vector that is a little bit more expensive, but that's kind of the same idea. If you pass this already pre-assigned space of memory to the BApply function, then it will be more efficient in terms of memory, no copy or duplication or appending, but also more, it will be faster as well. Okay, just a technical or performance tip comment if you wish. Now let's look at one of the other apply functions. This is the apply function. It's used for matrices or multidimensional arrays in this case. And you will notice that here the nomenclature is a little bit different. We are still using the object that we want to apply the function and the function, but in addition to that, we are going to add 1 argument, which is margin. Margin equal 1 means that we can apply the function per rows, or margin equal 2, we can apply the functions per columns. So let's create a matrix here. In this case, numbers 1 to 9 with 3 rows and 3 columns. So it's a 3 by 3 matrix. It looks like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's say I want to compute the maximum per column and per row. Okay, so I want to get which is the maximum value in each of the columns, which is the maximum value in each of the rows. How I will do that? Well, again, think how you will do this, how you will implement this with the tools that we have learned. Probably the best way is to loop over each row, slice the matrix per row, and then ask what is the maximum of the vector that compose each row, and do the same per column. But instead of looping, we can use the apply function. So if I do apply to the matrix A by row, that's what margin 1 means, and then apply the function max, what does is return the maximum value per row for each of the rows. So 7, 8, and 9 in this case. If we do the same per column, margin equal 2, then returns the maximum value for each of the columns. So no looping needed in this case. Okay. Any questions about this? Okay. Another example, same matrix. I'm not changing anything here. In this case, I'm showing you how you can apply two rows to the rows and the columns at the same time, which in other words is nothing else than element-wise. At each element, applying the function at the rows and the columns at the same time is the intersection of these possible rows and columns. It's applying to each of the elements in the matrix. And what I'm doing here is something called inline definition of the function. So instead of defining a function, I'm writing function which receives an argument. The argument is going to be each of the entries in the matrix. That's what these apply functions are doing, are feeding into the arguments of the function that I define the elements coming from the vectors, the matrices, or whatever I want to use. So in this case, I'm going to take the square. This is nothing else than just taking the power of 2 of each of the elements. Of course, you can do this with the star or hat operator, but this is just an example of how you could implement an element-wise operation using the apply function. Okay? Any questions about this? So let's talk about the apply now. This is another of the apply family functions. This is in general is a function that can be applied to each cell of a RAG array. An array is an irregular array. Bottom line is a subset of data from a data frame. That's the most generic case, or more general way of seeing this. And for doing that, I'm going to show you with some of the data frames that are available in R. In particular, I'm going to use the one called Marley. Marley is nothing else than records from the Michelson-Morley experiment. If you have taken any relativity courses or electromagnetic courses for what matters, you may remember that Michelson and Morley created an experiment with an interferometer, a light interferometer, which tries to determine which was the velocity of the light in the ether. The ether was the medium that people thought the light traveled, or electromagnetic waves travel, before Einstein's theory of relativity. So it was a very important experiment for determining that actually the velocity of the light in the ether was the same as the velocity anywhere in the Earth. So that basically put a nail in the coffin of the theory of the ether. So this experiment, what measure is, as I say, it has different repetitions of the experiment. Let's take a look at the structure. So I'm putting in a variable called data, the data frame from the Morley experiment. Again, this is part of the R built-in data sets. It has 100 observations with 3 variables. It has the experiment number, and then it has, I think, 10 runs per experiment. And then it has the measures of the speed of light in, I believe it's mile per hour or something like that. And there are some variations, statistical variations, something like that. But interesting thing is, okay, what about if we want to get the mean value of these experiments categorized by experiment number, for instance? And knowing that each experiment has 10 runs, how this will look like? Well, we can use the t-apply function. And in this case, as you can see, the data frame has a field called experiment, has a field called run, and then the speed, which is the actual measurement of the speed of light. So I can say, okay, from the data, give me the speed related to each experiment. So our second entry in the t-apply function means categorize or subset the data based on this entry, and at the end, apply this function. That is what the t-apply function is doing. So it's applying to the field data speed aggregated by a data experiment. And now you can see 5 columns or 5 results, 1, 2, 3, and 4, and 5. That's the experiment number. And then what was the mean value of the speed measured in each experiment. This can be done, again, think about how you will do it if I don't tell you to do it with TApply. You will have to go and, for instance, if you have been working assignment 3, maybe get the unique entries in experiment and then loop over each of the unique entries and then take the mean of the speed, slice it by the unique entry of the experiment number. That will be a way. Easily is 4 or 5 lines of code plus the complexity of the logic there, when we can get exactly the same result way faster, I can guarantee you that, with just 1 line of code. That's the power of these functions. So similar results can be used also or obtained with the split function, which basically split the data, for instance, data frame based on the column data experiment. But again, you will need a vector and then do some gymnastics there, manipulation to obtain the mean values associated to each of the split data subsets. Okay. Any questions about that? I show you another example of the TApply, but any questions about this? Is more or less clear? Another example of the TApply, maybe closest to your area of research, is to look at DNA's ELISA dataset. So this is an assay for recombinant protein DNAs, and again, this is a dataset built in R. It's called DNAs. And if you look at the structure, it has a run, and then the concentration of the protein, and then the optical density of the protein. So in this case, if you look at the data, as I say, you have different runs, different concentrations. This is the control variable, meaning that the independent variable, you can adjust the concentration, and then you look at the density or the optical density of these substances. And let's say that in this particular case, what we want is to compute the mean and standard deviation of the optical density, because it's what we measure in the experiment, for the given values of the protein concentration. That's the variable that you control in the experiment. So how I will do that? Well, very similar as we did before. Our variable to look for is DNA's density. Our independent variable or control variable is the concentration. And then the functions we want to apply is the mean and the standard deviation. So in this case, what we see is 2 rows. And these rows at the top, here and here, are the ones associated for the independent values of the concentration. So TApply went and looked into the unique entries again of the independent value of the concentrations, and then apply either the mean or the standard deviation function to each of these subset of data identified by the particular value of the concentration of the protein. Again, I found this to be super useful. One-liner, what we call super clean code. After you get familiar with the nomenclature and the arguments in the functions, are super straightforward to read as well, but more importantly, super efficient. Okay. And again, think about how you will solve this question, how you will implement this question if you had to do it without any of these tools. All right. Okay, any questions about this? This completes the apply family functions. Let me see, we're at the 2 sharp. So maybe it's a long description for the assignment. So maybe we can move into the assignment. What is left for next class, just to give you a little bit of a teaser, is how to create models in R. And again, I really would like to hear about you guys if you're interested. I tell you what I have planned for the rest of the class. So next class is going to be a statistical model in R, but building just linear models. Linear regression models, that's what we are going to see in next class. But I could expand, and that will take probably a good part of the class. That will be class number 9. Class number 10 is visualization, creating professional plots for your papers using R. Class number 11 will be visualization, doing interactive visualizations, where you can basically take a plot, your data, create a plot and display in your browser, but actually hover over the browser and create some really cool interactive display of the data. And class number 12, it could be machine learning, it could be high performance R, it could be something else, neural networks if you want. But anything of this can be changed. And the topics that you can be selecting, and again, depends what is your field of interest, we can do some generalized models. We can do model diagnostics for checking the sanity of the models that you generate. That will be interesting to have as a selection immediately after the next class, because it will be a nice continuation of this one. What else? It could be, as I say, specialized topics like survival analysis. I don't think anyone will be interested about that. Again, it can be machine learning. It can be, and when I mean machine learning, to be more precise, we can talk about techniques like decision trees or clustering, clusterization algorithms, those kind of things. Again, if you have any feelings, anything that matters to you because you feel that could be more interesting because of the research that you are doing, just do let me know, okay? You can email me, post something in the forum, whatever is your preferable way of communication with me, all right? All right, so let's talk then about assignment number 4. By the way, how are you guys doing with the assignments? As I told you, I don't think the email went out, by the way, but I graded and posted the submission for your assignment number 2 early last week. I think we were having an issue with the website, and I'm not sure if everyone got the email, but your grades have been posted there for more than a week, I believe now, or something like that. And as I told you, everyone was doing very well. But do let me know how you guys feel about the assignments, the load, and from what I'm reading from your submissions and your grades, everything is going well. Let me know if the pace is too slow as well. Let me know if you're getting too bored in the class. Anything that you guys want to let me know to try to change the pace of the class or the way that we do the class, okay? Okay, think about that and do let me know, right? Okay, assignment number 4. This continues to be along the lines of COVID. And what we're going to create is, and we're going to implement, is one of the most powerful techniques developed in the last century in computational science, in scientific computing, if you allow me. It's what we call the Monte Carlo technique. Monte Carlo technique is a way to actually compute things by sampling randomly certain distributions and then imposing some constraints on the distribution, imposing some regulations on the values that we take, and then basically counting. That's at the core of the technique. And it's very powerful. We are going to implement in what we call a nation-based model for modeling how disease and infectious disease like COVID can spread in a population, but it can be used for many other things. It can be used for determining probabilistic behaviors of different situations. It can be used for determining steady state solutions for chemical problems. A great variety of different disciplines use Monte Carlo techniques. So what we're going to start is a little bit verbose because it tries to be very, very detailed in the description and in the guidance of the problem. But what we're going to do is create a utility files as usual. There is a lot of text trying to explain why we do certain things or why you are going to be doing. And then each of these parts is to create a different function. So for instance, the first function, and I'm allowing you to call these functions as you wish, okay? So some freedom in the naming of the functions. Bear in mind to keep the names representative of what the function is achieving or trying to do. So the first function will take 2 numbers, 2 integers, and the function will create an initial vector of infection status. And what it means is this will represent a number of persons n, and then the second argument k will represent how many persons, how many people from that vector of n are infected. So let's put some numbers. If n is 10 and k is 5, then I have to represent with ones the persons that are infected in my vector of 10. So it can be 1, 0, 0, 0, 1, 1, 1, something like that. So 1 represents infected people, 0 represents healthy people, okay? Now the trick here, is those should be random, okay? So I will strongly recommend to look at the sample function. The sample function we saw several lectures ago. Look at the sample function and think how you can put k ones in a vector of n entries randomly. That's what this function has to do, okay? That's the first function. The second function is a function that takes a number of entries n, again, number of people, and then returns a vector of probabilities. And these probabilities represent the probability of infecting someone, infecting a person, I, that another person get in contact with. Now, these probabilities are determined by these values. 0.01 representing that this person is using a N95 mask, 0.05 representing that that person is using a medical mask, non-chirurgical mask if you wish, and then 0.1 if the person is not using a mask. So it represents mask behavior in the people, okay? Now, these are values by default, and the function, let me see, will divide this in 1/3. But again, these are the default values, and this should be represented in the vector of populations randomly. So what it means is if you have, for instance, let's say 9 entries, 9 people, 3 of them will have a 0.001 percentage of infection, 3 others will have 0.05, and 3 others will have 0.1. But this should be randomly shuffled between the 9 people, okay? Again, the sample function is a good way to think about this. Now, these are the default values for the distribution of probabilities within the people. I want to also have in the function optional argument where we can change that, because this is what we are going to do. We are going to be playing with this percentage, okay? So this function will have 2 arguments, one for the number of people and a second one for indicating the probability distributions of these individuals within the population. Okay, let me know if you guys have any questions. I know that this is probably the first time that you are looking at this, so questions may arise later, but do let me know. So the third part of the function is how the interactions happen and how the dissipation or diffusion of the disease happen. And for that, we are going to create a matrix. This matrix is a matrix representing interaction between individuals. And what it means, if the columns will represent people, the rows will represent people. And then if people I interacted with people J, then it will be a 1. If people I did not interact with people K, in the position IK, there will be a 0. So it's a matrix with zeros and 1. Now, we are going to say that person I doesn't interact with itself. So basically, the diagonal of that matrix is going to be 0. This matrix is going to be symmetric as well, because if person I interacted with person K also interacted with person I. So for symmetrizing a matrix, you can use this formula. I'm just telling you, for symmetrizing a matrix, do A lower triagonal A and assign the transpose of A lower triagonal A. Don't worry where it came from. I can explain to you, but just use this prescription for symmetrizing the matrix, okay? And remember, the diagonal has to be set to 0. Look at the diagonal function. We talk about this function when we talk about matrices as well. So that's the third function. The fourth function is where the actual dynamic of the interactions will happen. And what this will do is stated in this bullet point. So just go step by step. But basically, based on the previous functions, you are going to determine how is the probability of a person of getting sick, okay? Now, don't get into using any of the P functions we talked today. This probability is based on the results that you obtain in your own function. So you don't need to use P norm or Px, okay? Just use the functions that you used before. The last function is to basically evolve this in time. So this is for one single interaction between the individuals. The last function is for doing this for multiple times. So this function will take 4 arguments. These 4 arguments are cascade down to the other functions. But basically, one of the arguments is how many times we want this cycle to continue. Okay? Now, this is a parenthesis here in the assignment, is to explain to you a little bit how the sample function works. And take a look at the example, play with those numbers, play yourself, but this is how you can specify the ratio of the probabilities. Now, bear in mind that this vector that we are passing to the sample function has to add to 1, because 1 is the largest probability you can have. right? So play a little bit and see how changes the distribution of numbers that you get. Now, for the second part of the assignment, where we are going to create our main library script, obviously we are going to be sourcing our utility files, and then we are going to create a function that basically executes the process of simulating two cases: mask, where we have certain probabilities of using mask, versus unmasked case, where we have certain probability of people not using, the majority of people not using mask. So what we are doing here is changing the probabilities or the distributions of this 33% that was given by default in the second function. So we're going to have a function that receives one argument. I'm showing an example here. We're going to source the main driver script and then call the function COVID-19 analysis with the mass vector, and then it's going to inform us it's using the mass vector, and then it returns the results of the people that get infected. There are certain values. These are to 500 persons, so and 20 iterations. Okay. Now, what I also want you to do is that you run both cases and compare the results and see what do you see different between these two results, and add a few comments at the end of your main driver script. Of course, for the functions, we want to see comments, documentation of the functions, and for the function in the main driver script, defensive programming in terms of the argument. So the argument can be masked or unmasked, but nothing else. Okay, so the script has, or the function has to be protected against that. What else? One more thing, if you don't get exactly the same names, don't get worried, because remember, this is random, so it's expected to have some variations in the values that you get, although the trend should be quite similar to the one that you are seeing here for the masked case. Okay, due date is as usual 2 weeks from now at midnight. Any questions about this? Okay. All right. Again, we will have office hours on Friday. Feel free to post questions in the forum if you have any, or by email. And again, feel free to let me know if you guys have any particular interest in what topics to cover in what is left of the course. Okay. As well as let me know how you guys are doing with the material and the assignments and so on. All right. Okay. So if you guys don't have any questions, then I think we are done for today. I will see you then on Friday for the office hours. And again, if you have questions, don't hesitate to email me or post anything in the forum, okay? No problem, guys. I see you later.